All right, welcome back. Today's going to be the last video that we're going to do for the Organic Chemistry 2 sequence. For my students, we're going to leave it. We're going to do amines, and we're not even going to give it the full chapter's worth of treatment. We're going to talk about a little bit of it, and then we're going to leave it there. Some courses will go beyond me, and some courses won't get this far. So amines are functional groups that contain trigonal pyramidal molecular geometry on a nitrogen. So it's NH2, or it could be that's a primary amine. It could be it could be NH, that'd be a secondary amine, or it can be a nitrogen surrounded by 3 R groups, that'd be a tertiary amine. And we'll show you some examples of that here in just a second. So at the end of the day, there is a lot of good chemistry, neat chemistry that happens with amines. They're commonly found in plants. They were definitely isolated from plants early on, as we called them alkaloids, because we could use acid-base extractions to get them out. And you know, you're going to find that most of the things that you enjoy have amines in them. We could summarize that by saying that dopamine and serotonin are the only 2 things you actually enjoy, and of course those are both amines. And so we'll go into naming. We'll do a little bit of reactions of amines. We'll talk a little bit about the basicity of amines. And we'll leave it there. So we'll take a light treatment of amines here at this point, and we'll leave it at that for this particular video. So let's jump right in with some nomenclature. So what? All right, there we go. So when it comes to amines, amines are pretty low functional groups. So they're lower than alcohols. So that means they're lower than ketones, aldehydes, carboxylic acids, amides. And the only thing they're not lower than is esters or ethers. And so everything else, it's going to be higher than them. So that means amines are going to appear a lot as a lower priority substituent group. And so we'll have to really focus on both the naming of amines and naming of other compounds when there's an amino group in there. And that's the name of the substituent. It's an amino substituent. So when it's the parent, it's an amine. And when it is the substituent, it's an amino group. So let's take a look at a quick 5-carbon example. 1, 2, 3, 4, 5. Let's add NH2. So this would be a primary amine. And that's a primary amine because there's only 1 carbon attached to that nitrogen. We'll show you some examples of some secondary and tertiary amines, but at this point you should know that certainly from creation of imines and enamines. So let's take a look. This is a 5-carbon molecule. 1, 2, 3, 4, 5. We're going to name it with the priority with the number 1 carbon near the priority group. So that's the amine. So this would be 1 pentanamine, or of course you could call it pentan-1 amine. Let's take that same thing and let's add let's make it a ketone. And so now all of a sudden it's not the priority group. Now it's a substituent. It's still 5 carbons long, so it's still going to be a pent of some type. But now the numbering is different because the priority group becomes the carbonyl group. So this is a pentan-2-one or 2-pentanone. And it has an amino group at the 5 position, so it's 5-amino pentan-2-one or 5-amino 2-pentanone. Remember, there's dashes in between numbers. Okay, so that's a primary amine. Let's take a look at a secondary amine, because if you have secondary amine, then you have a carbon attached on more than one carbon attached to the nitrogen. And so it just becomes a little bit more of a challenge to sort out what's the parent group and what's the substituent group. Well, you won't be surprised to find that we're going to use the same method that we have before, and we're going to count the longest carbon chain. That's going to be the parent. So the longest carbon chain in this case is 1, 2, 3, 4, 5. Let's go ahead and make it 6 just to be different, versus 1, 2, 3. So obviously 6 is higher priority. So this is going to be the parent group. 1, 2, 3, 4, 5, 6. And so what do we call this now? This is a propyl group, but it's now at a new position, so it's at the N position. Just like we did with amines, substituents that are attached on the nitrogen will be located with the N locant. And so we want to then put everything together. Here's a methyl group. Let's not forget about that one. It's at the 2 position. So putting it all together, N or P, which one comes first? L-M-N-O-P. M comes first. So 2-methyl N propyl. And then we said it was a hex N1 amine. And you do have to have a location for the actual nitrogen group, because it doesn't have to be located at the N position, or excuse me, it doesn't have to be located at the 1 position. Here's an example of a slightly more complicated molecule. Let's have this one. Okay. So what do we have here? We have 1, 2, 3, 4, 5, 6, 7, 8 carbons. This is the group that gets us to the nitrogen the fastest. The 8 carbon chain is longer than the 2 or the 1 carbon chain. So that octanamine will be the parent group. And I also have a 4-methyl. So I have a 4-methyl. What else do I have here? Oh, it looks like I have an N-methyl. So that should be then N4-dimethyl. And then this is an N-ethyl. And so we're going to put this together just like we would in any other situation. It's an octan-3-amine. And it has, what comes first? E or M, or wait, do we use D? Which one is it? Well, remember, we're not going to use the D unless it appears in parentheses. So it's E versus M. So N-ethyl, N, 4 dash dimethyl. And let's just make sure I'm doing this absolutely correct. This is not a capitalized O. Dimethyl octan-3 amine. Okay, so this is a treatment of how you do amines. This one is an example of a tertiary amine, and the one we did before was an example of a secondary amine. Okay, so everything else with naming is the same. If there's stereochemistry that's specified, certainly this is a chiral center. This is a chiral center as well. I didn't specify the configuration of the chiral center by using a wedge or a dash, and so you don't need to include it because it's not specified. But if it were to be specified, then you'd need to include it. Okay, so let's move on down the road then. Let's talk a little bit about the properties of amines, and real quick, just so we're all on the same page. We know that amines have hydrogens as long as they're primary or secondary. So something like propylamine has a boiling point of about 50 degrees C, where something like propane has a boiling point of about -42 degrees C, and then something like propanol has a boiling point of about, say, close to, what is it? I think it's around 75. Let's just see real quick. Wow, it's pretty far off there. It's not 75. It's more like approximately 95 degrees Celsius. So when you got 3 carbon molecules, what's really happening here? This one is no hydrogen bonds. This one has hydrogen bonds, but it's to the nitrogen, and the nitrogen is a less electronegative atom. So the bonds here are going to have hydrogen bonds as well, but it's a more electronegative atom. Plus, when we take a look at it, this one only has 1 lone pair. This one has 2 lone pairs. So there's just more opportunities for the OH to do hydrogen bonding than there is for the nitrogen. So that's why we see a huge increase from just good old propane, but compared to propanol, propylamine is quite a bit less stable or has a higher vapor pressure. Okay, but there's one thing that amines do that alcohols don't do too well, and that's act as a base. And so we know that ammonia is a fairly good base. It can react with water and produce hydroxide. And NH4 plus. And this happens, while not to a huge degree, it happens enough that it's an appreciable reaction, that a solution of ammonia is considered a basic, will be a basic solution. And so let's see, what's the pKa of something like this? 1, 2 carbons, 1, 2 carbons, 1, 2 carbons. This one is triethylamine. And if we see triethylamine, we mix it with water, we can get some OH minus, and we get some of this positively charged nitrogen group. pKa here is about 10.8. We know the pKa here is 15.7. So the equilibrium does favor the side that has the water. That's the weaker acid, but it's only 5 orders of magnitude different. It is a strong enough base that you will find it used to do some basic reactions. Okay. All right, let's review some amine reactions that we know. So these will be reactions that produce amines. We know some of these already. If we take a alkyl halide and we react it with sodium cyanide, then we know that we'll get an SN2 reaction where the halogen is replaced with a nitrile. And at this point, we know that we can reduce a nitrile with lithium aluminum hydride, and that would produce an amine. So that's a review of a reaction that we know. Another reaction that we know is actually not a reaction, but a sequence of reactions. If we take a carboxylic acid and react it with SOCl2, then the hydroxide gets replaced with a chloride, and so that makes an acid chloride. Then if we react that with excess ammonia, we can make the amide. Then once we have the amide, we can also reduce that with excess lithium aluminum hydride. And that gets us an amine as well. I'll remind you of the reaction that we use to create aniline. So we can start with benzene. We can react it with nitric acid, H2SO4, and we will get nitrobenzene. And if we take nitrobenzene and reduce it, there's several ways to do that. We can do H2 and platinum catalyst. That'll definitely get us amine. So now we've got aniline. We can also do this with iron or zinc or tin or tin chloride, and then react it with sodium hydroxide. It does the same thing. We end up with aniline as the product. Okay. Now, we could theoretically prepare an amine directly from ammonia with an alkyl halide. So let's take methyl iodide. So we can get a SN2 reaction to take place, and we can form a salt that involves it would be a salt. It would be an iodine salt that involves a positively charged ammonia. This is all well and good, except that this species is more reactive to the SN2 reaction. So what happens is you just get this going on multiple times until you end up with your nitrogen fully alkylated. This is exhaustive alkylation. This would be a quaternary ammonium salt, and it's a salt of iodine. And so that's not particularly useful. So it's not really helpful to produce amines in this fashion. If you wanted this quaternary ammonium salt, it would work just fine for that. But really what we want to get to is the synthesis of amines. And so there is a way that we can do that with a substitution reaction. If we take an alkyl halide and we react it with sodium azide, and sodium azide is a molecule that has three separate nitrogens. And so there's an interesting situation here. It's got a negative charge. You have two formal charges on nitrogens of negative and one formal charge on the other nitrogen, the central nitrogen that's a positive. And that's why it comes in the form of a salt. So you can get azide to react with an alkyl halide in a regular old substitution reaction. And so then what are we going to do? In this next step, if we react it with, let's say, lithium aluminum hydride followed up by some water, we can then produce an amine, and we can produce an amine without adding any additional carbons. When we add cyanide, we do add a carbon. So sometimes we want to create an amine without adding carbons. And so there is a mechanism associated with this that you guys should know. And so we now have this species here. And so there's still a positive charge here and a negative charge there. We've created an overall neutral species, but the halogen ion is now what balances out our previous charge. If I have aluminum hydride around, then aluminum hydride can attack the nitrogen here. And now take a look at what happens. We're going to get this pair of electrons relieving our octet problem on the other nitrogen. So then what happens? How do we proceed further? Well, what drives this reaction forward is that we can expel nitrogen gas. And as a gas, it leaves the system, and that's what pushes the reaction forward from a equilibrium perspective. And then with the water, we can come along and reprotonate the amine, and that's how we end up with our product. And so this is a mechanism that I would expect you to know, along with the reactions that we've just discussed. But this will be it for the reactions of in amines as far as new mechanisms are concerned. Okay, here's another interesting synthesis that also involves SN2 reactions, and that's called the Gabriel synthesis. Now, the thing with Gabriel synthesis is that it involves a particular reagent. This reagent is potassium phthalimide, and it looks like this. It's got a benzene ring on one side of it, and then a 5-membered ring with a heterocycle nitrogen and 2 carbonyl groups flanking it. This makes this hydrogen fairly acidic, and so you could react it with a fairly straightforward base like potassium hydroxide, and you can get it to leave that hydrogen behind and form a negatively charged base. All right, and so this forms a salt of potassium phthalimide, and now the potassium phthalimide can go along and react with alkyl halides in SN2 reactions. So if we react this species with, say, something like this, then we'll get a regular old SN2 reaction where one of the electrons attacks that carbon and we lose the halogen. So what do we get? We get And this one has 1, 2, 3, 4, 5 carbons. So 1, 2, 3, 4, 5 carbons. So we get a species that looks like this. Well, this thing isn't particularly interesting. I mean, other than it is interesting, other than with respect to the chemistry, but it's not interesting with respect to what it's being synthetically practical. If we can get this guy to release the amine, then we could produce something we'd be interested in having, and we can do that if we react this in the presence of azide, or hydrazine, excuse me. So we do get rid of our 1, 2, 3, 4, 5 carbon chain that has now a primary amine. And so this is called the Gabriel synthesis. And so when you see the Gabriel synthesis, this is another one of those situations where you might see it from the perspective of the alkyl halide. And the alkyl halide might be reacted with potassium phthalimide in one step, and then reacted with hydrazine in a second step. You might also see it from a different perspective. You might see it from the perspective of the phthalimide. So we can start by showing you the phthalimide, and we might react that first with sodium hydroxide or potassium hydroxide, and then react that with an alkyl halide. And then work it up with azide, and then that should create our R and H2 as the final product. Now the regular SN2 restrictions apply, and we can't create secondary, we can't use tertiary alkyl halides, and secondary alkyl halides aren't great, but they do work. Okay, so what else do we know of the reactions? So those are a couple of new reactions interspersed in between reactions that we already know. Let's go back and talk about some other reactions that we already know. Well, we can take a carbonyl group, and if we react it with H+ catalyst, remove some water, and then react it with ammonia, then we'll create an imine. And I'm sure you're not surprised to know that if you take this imine and you react it with a reducing agent, and let's use a different reducing agent. So we could reduce the ketone with sodium borohydride. The problem with sodium borohydride is that it would just reduce the ketone before it had an opportunity to make the imine. So we want it to slow down just a little bit. So if we add a CN group, we get cyanoborohydride. And this won't react with the ketone, but it will react with the imine. So if I react this guy with sodium cyanoborohydride, then the reduction product is the amine. And so we can make a lot of different amines in this fashion. So if I were to take this reaction, let's just have an arrow. Let's have an arrow here. Let's have an arrow there. And let's take something like propanone. And if I react it with ammonia, H plus sodium cyanoborohydride, then I get a primary amine. If I react it with instead of ammonia, I react it with a primary amine, then I get a secondary amine, and it will even reduce ene amines. So if I react it with a secondary amine, then I'll produce a tertiary amine as the final product. So it isn't really a new reaction in the sense that we do already know how to create imines and enamines, but we're going to add the selective reducing agents, cyanosodium borohydride or sodium cyanoborohydride, and that does selective reduction of the amine group. So that's reductive animation. Amination. Okay. So that gives us a lot of different ways to make amines. We can now make some primary amines with azide synthesis, with potassium phthalimide, with the Gabriel synthesis, or we can react ammonia with a carbonyl group to do reductive animation, and we can form some primary amines as well. And we've also seen some ways that we can get some secondary amines and some tertiary amines out as our final product as well. Okay, there's one last reaction that I want to talk about. So this is one reaction of amines. And so we did spend most of our time talking about reactions that produce amines. Some of them are certainly new. Some of them are either repeats or they're minor variations of reactions that we already know. And so what I want to do is I want to discuss elimination reactions of amines. So if I do elimination of an OH group, then I can make an alkene. Now, if I were to do the same thing with the NH2 group, then I can also make an alkene. The problem is that if I were to do this, one of the things that we've discussed is that this species is not at all a good leaving group. This is a bad leaving group. However, we did say that if I react this with methyl iodide in excess, then I would do this exhaustive alkylation. And all of a sudden now I have a positive nitrogen. And this one is a good leaving group. So if I were to react an amine group with excess methyl iodide, and then follow that up with a base, and the common base is silver oxide. Ultimately, the silver oxide replaces the iodine from the salt that's formed here. The silver iodide, if you remember your general chemistry solubility rules, will precipitate out as a solid, and that replaces the iodide now with an hydroxide. And the hydroxide can go along and act as a base and do a regular E2 elimination reaction. And this is the product that we get. So this is E2. But what else do we notice here? That this is not the Zaitsev product. This is the Hoffman product. And so what's going on here with the Hoffman product? Well, if we take a look, we're going to have two situations. We're going to have a situation where the base can react at this carbon or at this carbon and do proton transfer. Reminding ourselves that there's free rotation around this single bond, we'll see that this group provides a bit of steric hindrance to this location. And so these hydrogens are going to react faster. And so this is Hofmann elimination of an amine. And so that's the last reaction that I want to show you for the semester. I hope you find these videos to be helpful. I really want to focus on problem solving, and so make sure you take, I'm hoping that you take a look at this ahead of time so we can do some practice problems in class. I'll come along in a little while and I'll make some videos that have to do with some problem solving, but we're going to save that for another week and another time and place. And so look forward to those if you're still studying organic chemistry. Other than that, this is Organic Chemistry 2. Have a great one.